and welcome to today's class. For today we'll be studying radioactivity. We'll look at the definition of radioactivity, look at the different types of radioactivity, look at some radioactive elements, and of course consider the idea of nuclear fission, nuclear fusion, and then of course we'll do past questions, Jamb past questions involving radioactivity. So first things first, let's define radioactivity. What is radioactivity? So by definition, radioactivity is simply the spontaneous decay or disintegration of the nucleus of an atom of an element where it emits alpha particles, beta particles, or gamma rays, or a combination of any two or all three, and also energy. The energy given out during radioactivity is called nuclear energy, and of course it comes in form of heat. So the energy given is a heat energy, also called nuclear energy. Alright, radioactivity was discovered in 1896 by a French physicist called Henry Becquerel. Alright, so this Henry Becquerel, a French physicist, discovered the idea of radioactivity in the year 1896. Alright, and it's from this concept that things like atomic bombs are being made. The idea of radioactivity was used to counter John Dalton's theory. John Dalton's theory of atoms, which says that atoms can either be created or split or destroyed. Of course, this concept or this discovery of radioactivity by Henry Becquerel in 1896 actually distorted that theory in the sense that with nuclear fission, atoms can be broken down, and with nuclear fusion, atoms can be created. Alright, but we'll look at this much more later. Let's look at the types of radiation. Types of radiation. So from our definition, we said when the nucleus of an atom undergoes radiation, that three particles majorly are being released. Number one, we said is alpha particles. Number two, we said are beta particles. Number three, we said are gamma radiations. Or you can say gamma rays if you want to. Alright, so we have these three as three types of radiation from radioactive elements. By the way, elements that undergo radioactivity are called radioactive elements. So when they undergo radioactivity, any of these three is being produced. We'll look at the characteristic of each of these three, and then we'll proceed. Let's start with the first one there, alpha particles. Alpha particles are positively charged helium nuclei. They move at the speed of light and are relatively massive. They are slightly deflected in the magnetic field and have very little penetrating power. Example, a tiny sheet of paper. Alright, so that's the characteristic of alpha particle. Let's look at the second one, beta particles. Beta particles are high energy electrons and also travel approximately at the speed of light. They are relatively light and are strongly deflected in a magnetic field. They have good penetrating power and can penetrate several millimeters of aluminium. So that's like the characteristics of beta particles. Finally, let's look at gamma rays. For gamma rays, we said gamma rays are electromagnetic waves of very short wavelength which travels at the speed of light and are electrically neutral. Their masses are negligible. They give small or no effect to a magnetic field and have high penetrating power in air and in solids. Example, many centimeters of lead or lead block. So having considered these the characteristics of each of the types of radiation, we said for alpha particles that they are helium nucleus, for beta they are electrons, while gamma rays are simply electromagnetic waves. Also note that alpha and beta are called particles because they are relatively massive, so they have a bit of mass. That's why they are both referred to as particles. While gamma rays, the mass of a gamma ray is negligible. So we can say it doesn't really have a mass, or the mass is too small and hence becomes negligible. And that's why this is not gamma particle, it is gamma radiation, because the mass is almost nothing. Alright? We said alpha and beta, of course, they also travel at the speed of light. And we said for alpha particle, it is slightly deflected in the magnetic field. For beta particles, it is largely deflected in the magnetic field. I would say for gamma radiation, it has either no deflection or it has very small or negligible deflection in the magnetic field. So we'll draw two diagrams, one for magnetic field, one for electric field, and then we'll look at the deflection of alpha, beta, and gamma radiation in both electric field and magnetic field. Alright, so here's a diagram to show the deflection of the three types of radiation in both magnetic field and electric field. Now let's analyze this first. For magnetic field, now what you have here is your radioactive element. So what you have here, this one here is the radioactive element. This is the radioactive element. What you have here is the lead block. You have the lead block. The lead block is used to ensure that the radiation does not spread to the environment. Of course, we said the kind of radiation that has the greatest penetrating power is the gamma rays, right? So we use the lead block to make sure that the radioactive element does not spread that radiation to the environment. That's the idea. What we have here is the photographic plates. This is the photographic plate. What you have here is called the photographic plate. Right, so you have this. For the magnetic field, you observe that the alpha particle will be deflected, as you can see, towards the south pole, but it will be a slight deflection. So I have slight deflection towards the south pole in the magnetic field. But look at the gamma rays, it is not deflected, so it just goes like this. Or it is slightly like the deflection is almost nothing, alright? But look at beta particles, it is largely deflected. This is largely. This is largely deflected towards the north pole of the magnet, alright? So this is deflection of the three types of radiation in a magnetic field. Now, if we come over to the electric field, of course, this is still the radioactive element, this is still the lead block, this is still the photographic plate. Observe that the alpha particle, being positively charged, will go towards the negative charge. Of course, in obedience or in accordance to the first law of electrostatic, which says like charges attract. Alright? Also, the beta particle will also, which is an electron, being negatively charged, will move towards the positive region of the electric field. Now observe that when it comes to electric field, the deflection are almost alike. Alright? But in magnetic field, the deflection of the beta particle is large. Right? You can see it. Right? It is largely deflected in magnetic field. Right? While for magnetic field, alpha particle is slightly deflected. But when it comes to electric field, the deflection are almost like the same thing. For gamma rays, whether it's in magnetic field or it is in electric field, observe that there is no meaningful deflection. So this is deflection of radiation in both electric field and magnetic field. Alright, so let's proceed. Alright, so let's look at the types of radioactivity. Now, generally, there are two types of radioactivity. Number one, natural radioactivity. Number two, artificial radioactivity. So these are the two types of radioactivity. By definition, natural radioactivity is simply the spontaneous disintegration or decay of the nucleus of an atom where alpha particle, beta particle, gamma rays, a combination of any two or all three is being released with the release of heat energy. Now, the heat energy released during radiation is called nuclear energy. Now, when it comes to a definition for both natural radioactivity and radioactivity in general, we said it is the spontaneous decay or disintegration. Now, let's analyze the term decay. When we talk about decay in radioactivity, there are usually two types of decay. The first one is called alpha decay, and the second one is called a beta decay. Alright? During alpha decay, you have a particular element decaying or a particular element is being broken down to form a new element in which the mass number of the new element is being reduced by 4 and the atomic number of the new element is being reduced by 2, basically. While for a beta decay, the mass number of the new element remains the same, while the atomic number of the new element is being increased by 1. So this is the chemical equation for an alpha decay. Generally, when it comes to decay, for alpha decay, the general equation for an alpha decay is given by, let's say I have an element X having atomic number Z and mass number A. I have this. If this element undergoes alpha decay, of course, since it's an alpha decay, that means an alpha particle will be produced. And when we discussed alpha particles, we said they are helium nuclide. This is 2 here. So this is the nuclide symbol for helium. Plus, you have a new element being formed. Let's call the new element Y. For Y there, we said the new mass number becomes what I have here, A minus what I have here, 4. So you have this. Y for the atomic number, I have here Z. So it becomes Z minus what I have here, 2. Alright, so this is like the general equation for an alpha decay. And for an alpha decay, we said an element would disintegrate to form a new element such that the mass number of the new element would differ from this one by 4, and also the atomic number of the new element would differ from this one here by 2. Alright, this is just the general one. If you look at beta decay, the second one there is beta decay. For beta decay, the general equation would be this. So I have an element X having atomic number Z and mass number A. This is undergoing beta decay. Of course, we said for beta, we said they are electrons. For electrons, we have that the atomic number is -1 and the mass number is 0. Alright, for this it becomes plus a new element is formed, Y, such that now when it comes to getting the new atomic number for my new element, we said it was this one here minus this, so it becomes Z minus 2. With that same concept, for this it becomes Z, this one here, minus what I have here minus 1 becomes Z minus what I have here, so it becomes Z minus 1, and that's equal to Z minus gives you plus 1. I'm having Z plus 1 as the new atomic number, so it becomes Z plus 1. Yeah. Same thing here. This one becomes A minus 0, which is obviously A. Alright, so this becomes the major difference between an alpha decay and a beta decay. For an alpha decay, the new element form is such that its atomic number is being reduced by 2 and its mass number is being reduced by 4. While for beta decay, it's a new element is being formed such that the atomic number is being increased by 1 while the mass number remains the same. This is in its basic state, okay? That's if it emits just one beta particle and it emits just one alpha particle, I would have this. So this is like the simple idea behind alpha and beta decay. We'll take some examples to explain the concept of alpha and beta decay. Alright, so an example of an alpha decay is when radium-226 decays to form radium-222 as given by the equation below. So I'm having radium Ra having an atomic number of 88 and mass number of 226. So this element is called radium. It's a radioactive element. If this element undergoes alpha decay, it will produce helium nucleus, of course, He, such that here becomes 2 and 4, plus the new element form is called radon. So I have this here. For radon, they will say the mass number becomes this one minus this. So it becomes 88 minus 2. That gives you 86. Y for this one becomes 226 minus 4. That gives you 222. Alright. So Ra instead is called radium. Rn is called radon. Alright, so these are like two elements under radioactivity. Now, of course, we said it is spontaneous disintegration or decay, such that for this one, since it's an alpha decay, alpha particle is being released, and we said at the end you have an energy being released. Of course, we said it's heat energy. It becomes plus energy. All right. So whenever it comes to writing radioactive decays, all right, at the very end there should be energy there. So I have this. So this is an example of an alpha decay. All right. Let's take an example to explain beta decay. Also, let's get for beta decay. Let's take an example of beta decay. Now, one example of beta decay is that radon emits or undergoes beta decay to emit two particles or two beta particles to produce an isotope of radium. All right. So I have radon, that's Rn. Atomic number 86, as we see here, and mass number 222. This becomes 222. Okay, would emit two of beta particles. That's electron minus 1 and 0 to produce. Now the new element form here becomes 86. So say 86 minus 2 times this, that becomes 2 times minus 1, that becomes equal to 86 minus 2 times minus 1 is minus 2, and that's equal to 86 plus 2, and that's equal to 88. So the element that has atomic number 88, of course, as you can see here, is radium. So that means I'm having R here, radium, having atomic number 88. So I have this. For the mass number, it becomes this one here. So that becomes That becomes 2 to 2, 2 to 2 minus, of course, this was 2 times minus 1. This now becomes 2 times 0. That's 2 times 0. I'm having 2 to 2 minus 2 times 0 is 0. That gives you 2 to 2. So the mass number here becomes 2 to 2. So observe, this and this, they are both radium, having the same atomic number 88 and 88, but different mass number 222 and 226. So we can say radon undergoes beta decay to emit 2 particles of to emit 2 beta particles to produce an isotope of what? Radium. So we can say this one here is an isotope of radium. Now don't forget that in the concept of isotopy, we said an element has, or isotopes refers to elements that have the same atomic number 88 and 88 but different mass number 222 and 226. So they are different mass number. So we can say radon undergoes beta decay to produce an isotope of radium. And of course, plus, very important, energy. Plus energy. Alright, so this is how the concept of alpha decay, which is this, perhaps I should indicate this here. This is how alpha decay and beta decay works. We'll take more examples on alpha and beta decay and explain this point much better. Alright, so let's take this simple example to help us understand the concept of alpha beta decay. So this question says uranium-238 decays by emitting 2 alpha particles and 2 beta particles to thorium. Alright, so thorium is actually an element whose symbol is TH. They said write a balanced equation. Alright, so we need to write a balanced equation of this particular decay. Now before then, something for me to notice this. Decay or disintegration is actually a decomposition reaction, which means for a decomposition reaction is a kind of reaction where we have more products than reactants. So for this, first of all, let's get uranium. Alright, so let's get this done, please. So for uranium, the chemical symbol is U. The atomic number, of course, is 92, while the mass number is what you have here. So 238. Alright, so this undergoes a decay to give 2 alpha particles. So it becomes 2 times alpha particles, say they are helium. So it becomes helium, having 2 here, and of course 4, and also 2 beta particles. So it becomes plus 2 of beta particles. That should give you beta particles. We said they are electrons, so it becomes electrons. This is -1, this is 0. Alright, so I'm having uranium with atomic number 92 undergoing a decay to emit 2 alpha particles and 2 beta particles to form thorium, 3H. So it becomes plus, thorium should be TH, so I'm having TH. Alright, our task now will be to find the atomic number and the mass number of thorium here. Now of course, plus, obviously we have our energy. We have energy here. I've said the kind of energy released during radioactivity is called the nuclear energy, or perhaps heat energy. So let's get the atomic number and the mass number of thorium that will be released. Alright, so let's get, so this becomes 92. So I'm having 92. For this, since this is under decay or disintegration, it becomes a subtraction. So it becomes minus. Let's look at alpha decay. I'm having 2 times what I have here, that's 2. So I'm done with this one here. Come to the beta decay, it becomes also minus what I have here, 2 times what I have here, -1, and that's all. Alright, so it becomes 92 minus 2 times 2, also minus 2 times minus 1. If I work out this math, this gives me 92 minus, this gives you 4, minus, this and this gives you minus 2. So I have this. This is equal to, I have 92 minus 4, minus minus is plus 2, and that's equal to, so 92 minus 4 gives 88. 88 plus 2 gives 90. I'm having here as 90. So hence, for thorium, the atomic number becomes 90. So I have 90 as the atomic number. We'll do the same thing to get the mass number. So for the mass number, I have this as 238. So I'm having 238 minus 2 times 4. So 2 times 4 minus this times this. 2 times 0. So I'm having here as 238 minus 2 times 4 is 8 minus 2 times 0 is 0. So I'm having 238 minus 8, that's 230 minus 0, that's 230. So this gives you 230. So this now becomes the equation of the decay on the, where uranium-238 undergoes decay by emitting 2 alpha particles and 2 beta particles to produce thorium-230, having an atomic number of 90, and of course with the release of energy. So this is how this is done. Alright, so we earlier discussed that there are 2 types of radioactivity: natural radioactivity and artificial radioactivity. We've discussed the concept of natural radioactivity, citing instances using alpha decay and beta decay. Now when it comes to artificial radioactivity, in artificial radioactivity, it is simply, or we can say, artificial radioactivity occurs when an element which is usually not radioactive is being made radioactive by bombarding it with a radioactive substance. That is artificial radioactivity. So by definition, artificial radioactivity occurs when an element or a particle which is usually not radioactive is made radioactive by bombarding it with a radioactive particle. By bombarding, I mean combining it, alright, with a radioactive particle. That is artificial radioactivity. So an example of artificial radioactivity is what you see here. Here we have aluminium. Now usually aluminium is non-radioactive, alright, but if I combine, you can see here, aluminium is now combined or bombarded with helium nuclei and then thereby producing phosphorus, alright, phosphorus 30, which is being combined with neutron, which on further decay produce silicon 14 or silicon 30, having 14 as its atomic number. Now if you look at this one here, for the left hand side, for this one here, total atomic number is 15. Here, 15 plus 0, total atomic number is 15. Here, the same thing. Now see the trick here, alright, so in this case now, the electron now becomes a plus 1, such that I'll have 14 plus 1, giving you a balanced 15 as your atomic number. For this one here, I have this as 31, alright, so this is 31, the mass number combined, 14, 27 gives you 31 combined. Same thing here, 30 plus 1, that gives you 31. So for these two, mass number here, total mass number is 31. Here, total mass number is also 31. But here, total mass number is 30. So we can say some bit of energy, if right, is being lost. Is being lost in this process. So you can see here, energy is being lost at this point here. Alright, so because the mass number is gone. Alright, so some other examples of artificial radioactivity includes what you see here. For this one here, I'm bombarding lithium, alright, lithium atom with a neutron. such that it will now decay into, you have tritium here. Tritium is an isotope of hydrogen being combined with helium, that's alpha particle plus energy. Same thing here. For this one here, I'm bombarding, for this one here, the element that is not radioactive is lithium here. Same thing here. For this one, the element that is not radioactive is beryllium. But I will now bombard, I will now combine beryllium with my alpha particle, which is helium. It will now produce carbon, alright, carbon 12 with neutron, and of course, plus energy. Alright, so these are examples of artificial radioactivity. That's a case where non-radioactive elements such as aluminium, such as lithium, such as beryllium is now being made radioactive by combining them or bombarding them with radioactive particles. Okay, helium, neutron, of course helium. So this explains the concept of radioactivity. Now next up, we look at what is called radioactive isotopes or radioisotopes. Alright, so let's look at the concept of radioisotopes. Radioisotopes are simply isotopes of elements that are formed by bombarding certain elements with a neutron, a proton, or a deuterium. Alright? So when it comes to radioisotopes, they are simply isotopes that are formed artificially by bombarding a particular element with either a proton, a neutron, or a deuterium. That's the simple idea of radioisotopes. Now, for instance, we have these two things. We have cobalt here, we have bromine. Now, if I bombard cobalt 59 with a neutron, from here, if these two are combined, of course, looking at atomic number becomes 27 plus 0. Now, in this case, I'm not subtracting because this is not a decay. In this case now, you can see that there's a combination here. So I'm going to add up the atomic number and not subtract. So if I add up the atomic number, it becomes 27 plus 0, which is 27. So a new element of atomic number 27 is formed, which of course is the same element, that's cobalt. So I'm having cobalt here with atomic number 27. Also, for the mass number, I'll simply sum up this and this. So it becomes 59 plus 1, that's 60. So I'm having cobalt 60, and of course, with the release of energy. So this becomes a radioisotope. That's an isotope of cobalt. This is a radioisotope. For this one here, I'm having bromine 79, combining with a neutron. So if I combine this, of course, for the atomic number, it becomes 35 plus 0, which is still 35. So an element of atomic number 35 is being formed, which of course is still bromine. So I have bromine here. So bromine with atomic number 35. For the mass number, combined is 79 plus 1, that gives you 80. And of course, plus the release of energy. So I have energy is being released. Alright, so these are equations that shows the concept of radioisotopes. Alright, so cobalt 60 is a radioisotope of cobalt 59 because it was got by combining cobalt 59 with a neutron. Also, in the same sense, bromine 80 is a radioisotope of bromine, or for say bromine 79, because it is got by combining bromine 79 by neutron. So we can see cobalt 60 and bromine 80 are both radioisotopes of cobalt and bromine respectively. Alright, so this is just a simple concept of radioisotopes. Alright, this is just a simple concept of radioisotopes. Next up, we look at nuclear energy and the concept of nuclear fission and nuclear fusion. Alright, so let's look at the next concepts. They're called nuclear energy. Now, most likely, when you look at, if you refer back to our equations on alpha decay, beta decay, and etc., you observe that at the end of each radioactive equation or radioactivity equation, you observe that there's something called plus energy. There's always a plus energy there. So what's that plus energy? That energy there is called a nuclear energy. What's a nuclear energy? A nuclear energy is simply the energy that is released or given off during a radioactive process or during radioactivity. Alright? So when there is a radioactive process or when radioactivity takes place there, energy is being given up. That energy there is called a nuclear energy. Alright? We talked about, I just mentioned the concept of radioactive process. Alright? Basically, there are two basic radioactive processes, which includes nuclear fission and nuclear fusion. Alright? The two basic ones so nuclear fission and nuclear fusion are two basic radioactive processes. Alright, so by definition, nuclear fission is simply the splitting up of the nucleus of the heavy element into approximately equal parts with the release of a huge amount of energy and neutrons. So that's the definition for nuclear fission. Let's look at nuclear fusion. By definition, nuclear fusion is simply the nuclear process in which two or more light nuclei combine or fuse to form a heavier nucleus with the release of large amounts of energy. Alright, so we look at we use one nuclear or radioactive equation to explain two of them. Okay, so this is one example each for nuclear fission and nuclear fusion. Alright, nuclear fusion, nuclear fission. Alright, let's start with this. Alright, let's start with this. For here, I have a neutron being bombarded by or bombarded with uranium to produce barium, barium 141. Krypton 92 and 3 neutrons, of course, with the release of energy. So this is an example of a nuclear fission. All right. For the nuclear fusion, I have this is deuterium. That's an isotope of hydrogen being combined or being bombarded or being combined with tritium to produce the helium molecule with, of course, your neutron, of course, with the release of energy. Now, if I try to look at the atomic number and mass number involved, for the left-hand side of the equation, for under nuclear fission, for the left-hand side of the equation, if I try to sum up the atomic numbers, I have 0 plus 92, which is 92. For my right-hand side of the equation, I have 56 plus 36, which is about 92, plus 3 times 0, which is 92. So this is a balanced reaction or equation, because I have at the left-hand side of the equation, I have 92 total atomic number. On the right-hand side, I have 92 total atomic number. If I look at the mass number, for the left-hand side of the equation under nuclear fission, for the left-hand side of the equation, I have 1 plus 235, which is 236 in total. If I look at this becomes 141 plus 92. That's about 233, right? 233 plus 3 times 1, so it's 233. If I combine 141 plus 92, also combine this to 3 times 1, that's 3. That gives you 236. So I have here in total 236 as the total mass number. Here, so I also have 236 as the total mass number. So this is a complete, this is a balanced equation of nuclear fission. If you look at nuclear fusion here, right? Nuclear fission and nuclear fusion. If I look at the nuclear fusion reaction here, this is 2 in terms of mass number. This is 2 plus 3. So totally, for my left hand side, I have 5 as total mass number. If I look at the right hand side of the equation, I have 4 plus 1, that's 5 as total mass number. Also, if I consider atomic number, I'm having 1 plus 1, which is 2. From here, 2 plus 0, which is 2. So it becomes a balanced radioactive equation. Now, how do you easily know the difference between a nuclear fission and a nuclear fusion? What's the difference between them? The idea is simple. For a nuclear fission, I have a bigger element that is being split into smaller ones. Alright? While for a nuclear fusion, I have smaller elements being combined to form a bigger one. That's the idea. Alright, so this is how you can easily differentiate between nuclear fission and nuclear fusion. For nuclear fission, you have a bigger element with a higher mass number and a higher atomic number being split into several other elements with smaller atomic numbers. You can see here, smaller atomic number. So the larger atomic number is being split into what there? The smaller atomic number. Same thing with mass. The element with the larger mass number is being split to other elements with smaller mass number. So it becomes a fission, alright, a breaking off, alright, that's it. While for fusion, when something is being fused, it means it is being combined. So I have elements or isotopes with smaller mass number and smaller atomic numbers being combined to larger ones. As in this case, you can see the smaller ones, 2 and 3, being combined to form the larger one, which is 4. And also, you can see the smaller atomic numbers, 1 and 1, which are being combined to form the larger atomic number, that's 2. So how do I know if it's a nuclear fission or a nuclear fusion reaction? Fusion reaction, very simple. Look at the reaction very well. Where do I have the element with the larger atomic number and mass number? If it's at the reactant part, that's here, then it's a nuclear fission reaction. If the element with the larger atomic number and mass number is at the right hand side or the product part or the product side of the reaction, then it becomes a nuclear fusion reaction. Alright, so this is how you can easily differentiate between a nuclear fission and a nuclear fusion reaction. Alright, so we'll take some Jamb past question and we'll solve from here. So let's take the first question here. It says, when Pb, that's lead, when lead 210 decays to form lead 206, it emits dash. Alright, so the concept is simple. I'm having lead Pb 210 and of course 86, 82. Okay, they said this decays to form lead 8206. They said it emits dash. When it comes to emission, we know about alpha decay and beta decay. If I look at this, the difference here is that for my mass number, it has been reduced from 210 to 206. That means this one here was got by subtracting 4 from here. So 210 minus 4 gives us 206. So it has to be a particle such that here has to be 4, because 4 plus 206 gives you 210. Also, I'm having 80 here, I'm having 82. So here has to be 2, such that 2 plus 80 gives you 82. So that this becomes a balanced equation. And look at the particle that is 4 and 2 is helium. So I'm having helium here instead. Alright, so the answer has to be 1 alpha particle, because we said heliums or alpha particles are heliums. Alright, so it has to be 1 alpha particle. The answer there is option A, an alpha particle. Alright, this question says the radioisotope uranium 235 having atomic number 92, decays by emitting 2 alpha particles, 3, that should be beta, not bit, 3 beta particles, and a gamma ray. What is the mass and atomic number of the resulting daughter element? Alright, let's get this done. I'm having uranium-235. They said it's undergoing a decay, okay, so decomposition reaction. They said 2 alpha particles, so 2 alpha particles are helium, He, 2 and 4, and also 3 beta particles, so 3 beta particles are electrons, so electron -1 and 0, plus, and they said a gamma ray. Gamma is just this, there's no representation. They said plus, what is the daughter element, or what is the atomic number and mass number? Okay, it says mass number and atomic number of the daughter element. So daughter element here, mass number here, atomic number here, obviously plus, very important, nuclear energy. So let's get the values here. So how do I get this? So I'm having for this, let's look at mass number first. Here becomes 235, so 235 minus, that becomes 2 times 4, so 2 times 4 minus, that becomes 3 times 0, that's 3 times 0. This one does not really affect it. So I'm having this is equal to, I'm having 235 minus 8 minus 0, and that's equal to, I'm having 235 minus 8 minus 0, and that's about 227. That means the mass number here is 227. I'm done with this. Let's get atomic number. This becomes 92 minus 2 times 2 minus 3 times minus 1 minus, this one has an effect, so we can let it go. It's equal to, so I'm having 92 here, so it gives me 92 minus 2 times 2 is 4, so minus 4 minus 3 times minus 1 is minus 3, so I'm having minus 3. And this is now equal to 92 minus 4 minus minus is plus 3. This is equal to, this will give you minus 1, and here that should give you 91. That should give you 91. So 92 minus 4 plus 3 gives 91. So I'm having here as 91. It means that the daughter element is an element such that the atomic number is 91 and the mass number is 227. So that is the daughter element. So hence the answer is 227 for mass number and 91 for atomic number, and that is option C, 227 and 91. By the way, the element with atomic number 91 is called protactinium. Protactinium is Pa, that's the symbol, alright, that's Pa. This is an element that has atomic number 91. So you can say uranium-235 undergoes radioactive decay to produce 2 particles of alpha, or 2 alpha particles, 3 beta particles, and a gamma ray to produce protactinium-227. Alright, so this is how we solve this particular question. Alright, so this question says, what type of reaction is represented by the equation this? Alright, you have fusion, you have fission, you have change, you have ionization. So what's the answer there? Now, we've said before, it's easy to differentiate between nuclear fission and nuclear fusion. We said for fission, you have the particle or the element with the greater atomic number and mass number on. For fission, you have it on your left hand side, while for fusion, you have that element on your right hand side. If I look at this equation here, this is the element that has the greater atomic number and the greater mass number as compared to any of these here. So since this element is found on the right hand side, this becomes a nuclear fusion reaction. So the answer is fusion, because the element with the greater atomic number and mass number is on the right hand side of the equation. So that becomes option A, fusion. Alright, look at one last question on radioactivity. Now this question says the product of the decay of phosphorus 32 as a beta emitter is dash. Alright, so let's get this done. Okay, so let's get this done, please. So observe that the given element here is phosphorus. Now, usually when they say phosphorus 32, it means that the mass number is 32. That's 32 here. Now, observe, you were not given the atomic number because they are assuming that you should know. Alright, they are assuming that you should know the atomic number of phosphorus, which of course is atomic number 15. So I have 15 here as the atomic number. It said is undergoing a decay. So this of a beta emitter. Okay, it becomes beta emitter. That's electron minus 1 and 0. It said a beta emitter. That's just 1. All right. So what is the product? So plus all I have. We said for beta decay that the mass number is the same thing, so 32. While for the atomic number, we said it will increase by 1. Alright, so it becomes 15 minus 1. That becomes 15 plus 1, that is 16. Alright, so I'm having 32, 16. That of course is sulfur. So I'm having sulfur as the answer. So sulfur 32 with atomic number 16 becomes the answer. Alright, so that's how you get this question. That's how you answer this question. Alright, so that's the last thing for this class on radioactivity. But before we go, I'll give you one work. You have this reaction, sodium 23 11 combining with a neutron to give you sodium 2411 plus energy. Let's say energy. So leave a comment in the comment section. What is the name of this reaction? Alright, or what does this fall under? Alright, leave your answer in the comment section. See you in our next class.